Hello, welcome back to Energy 101. Today we're going to do an other lecture, talking about other energy issues and technologies. I didn't quite know what to call this, but it's a catch-all for the issues and technologies that some of you have brought up and that wanted covered. There just wasn't time to cover everything. This is the last week. But let me just make some general statements about them. How did I choose the topic? I think it's helpful to recognize how I chose the topics that we did cover. It came from the course objectives in that I wanted you to know where our energy use is going and what the demand is and why we have that demand. Wanted you to know where the energy sources are that we're getting them from and the conversion technologies. And then have at least some examples of how to assess in the process of assessing new energy technologies and deployment. So this is all about deployment, assessing what happens when you deploy new energy technologies, which we certainly hope will happen here over the next 20 to 50 years, including next year. So that was my purpose, and I always say we need to understand the $10 to $15 trillion infrastructure that exists in our energy system today. It's at least that, and we can't just bulldoze it all down overnight and replace it with something new. But we got to have a plan, and just in case I haven't made the point, that we need to do everything. We need, no matter how small or how big, we need to implement all the new technologies to reduce our energy consumption, increase our supply, increase our renewable energy, decrease CO2 emissions, and decrease particularly oil supply, but also, of course, for CO2, coal, and gas. So I'm going to talk about a lot of them here, so let me just race through them. Number one thing that's always a little frustrating to me is that there are an infinite number of ideas and suggestions that have been brought to me over the last 35, 40 years that I've been in the energy area. Particularly in the 70s, they started with the energy crisis in the 70s, which if you Google it and look back at it, had a dramatic impact on our lifestyle and culture, which I won't go into. But there are either they want somebody to assess their technology, analyze it, and develop it and build it. Because it's such a great idea, they're convinced it'll revolutionize the world. They just want to keep the patent rights and want somebody else at no cost to them to assess it and develop it. Obviously, that doesn't work in my situation anyway. I don't have those resources available to me from the university or otherwise. But a few of them also are building prototypes, but they're not quite running. They won't work, but all they need is a few $1 million more, and because they generally have raised a lot of money in some cases, and to amateur investors that they convinced would work. But the ones I hear about most, they immediately are recognizable as violating the natural laws of nature. For instance, engines running on water, hydroelectric power generators that have more than 100% efficiency, violating the conservation of energy law, that you cannot create or destroy energy. Engines running off of magnets, that's the really popular one. That is free energy because you can get it from magnets and you won't demagnetize the magnet. It'll just run forever for perpetual motion. And often they have patents, but having a patent, people think because you got a patent that it means it'll work. Patent office does not substantiate that it'll work. They merely substantiate that it's unique compared to other patents that are out there and other technologies and ideas that are out there. Regarding engines running on water, I always like to tell the story. I've been in that one for a long time. When I was a teenager, I had a friend that had an old car, and the fuel tank, gasoline tank, rusted, and it would get rust in the carburetor. So he just disconnected the fuel tank on the car and put a 5-gallon can in the back floorboard. Back then they had enough floorboard space to do that in the back, and put gasoline in there and just ran the gas line in there and pumped it out of there instead of out of the tank. And so one Saturday afternoon, we mischievous teenagers didn't have enough to do, so we'd go around to all the filling stations in the town, and they were self-service. Full service back then. Nobody pumped their gas, and we'd pull up and they said, "Can I help you?" And said, "No, we just need some water," and we'd get the water hose and put water in the fuel tank. And then we had an aspirin bottle that we had taken the labels off. When we'd take a pill out and we'd throw an aspirin in there, then get in and drive off. And we thought that was hilarious, that we were trying to make people think we were running a car on water. But that's been around for a long time, and I've gone to look at projects over the years. I could write a book on the projects that I've looked at, including nuclear-powered engines. One in Daytona, Florida, that had raised a lot of money from amateur investors, like $1 million or so, and that claimed it was running off of nuclear power. But none of those ever proved out when I looked at them and was able to have the time and money to make an assessment of it. But unfortunately, all these ideas keep coming back because negative assessments are never published. You don't publish in the science journal or engineering journal or popular journal negative assessments. And as soon as you make a negative assessment, someone will make a small suggested change to it. That means you got to start all over again, do it again. But they never do the assessment. They want you to do it. And so it is problematic. But there are an infinite number of them, and we can't cover an infinite number in this course, obviously. Can't even cover a finite number. But let's just look at a few of them. I'll make some comments. The first one being energy use, efficiency, and conservation. This is a huge opportunity. But from the beginning, every one of these issues here are public policy issues. They're not technology issues. We have the technology to do all these things, and they're developed, and all you got to do is just have a market for them, and we'll have it. But first one, which I've been involved in since the 80s, early 80s. I'm not doing it anymore, but in existing factories and buildings, to reduce their energy consumption by going in and doing energy audit. And in many cases, with no dollar spent, merely making adjustments on settings, you can significantly, like 20%, reduce the energy consumption of the factory or building. And you say, well, that's wonderful. You do that once and it's done. But you can't do it once, because if you go back in a year, you find that all the adjustments are out of kilter and they're using as much energy as they were before. So it's an execution and management problem again. It's not a technology problem. And I'm a technologist. I'm not a public policy person. I'm not a politician. So I try to stay to technologies and assess the impact of those technologies on our energy consumption and our infrastructure and our CO2 emissions. An example are appliances, that refrigerators. That's a beautiful example, and it's brought up many, many times of what we can do. Refrigerators today of the same size use 3 times less electricity than they did in 1975. How did that come about? Well, it came about not by free marketplace, unfortunately, even though the economics were very positive. By spending a little bit more money, you could always get a little more efficiency. But they were accomplished with the Congress passing U.S. efficiency standards that are set by, or the ability for DOE to set those efficiency standards and apply minimum efficiency standards to any refrigerator that is sold and was sold, starting in the 70s. And today, they're using 3 times less over 35 years. And with that technology that was available in the 70s, it's available now. Heat pump water heaters is another one that hasn't been as popular as refrigerators, because that one was mandated. Heat pump water heaters were not mandated. But heat pump water heaters, to use the heat pump effect, compared to electric water heaters, they'll save 50% of the electricity used to heat water. They bring the operating cost for electric resistance water heating down to about that of natural gas. So they don't, heat pump water heaters don't compete with natural gas water heaters, but they will save about 50% compared to conventional electric water heaters, including instantaneous water heaters. And I could go on and on with appliances. But that one merely, heat pump water heaters merely, the economics are very good. Typically a household will spend $600 a year for hot water heating, and heat pump water heaters are on the order of $1,500, so it's a 2 to 3 year payback, and better than that in some areas like Hawaii or California high cost electricity areas. Regarding auto efficiency, that's another example of that was accomplished by U.S. EPA standards when they were first imposed in mid-70s. Average auto efficiency was 13 miles per gallon. That improved to about 28 miles per gallon due to standards set by the EPA, and but they didn't change from 28 for about some of the mid-80s or so up until the mid-2000s or late 2000s. So we went about 20 years without increasing that, even though Europe has had the technology there for many, many years because they have more economic incentive, but they have a large tax on their gasoline and diesel fuel. So those, again, are examples that have been done and can be done, but they're public policy issues. None of these are technology barriers. We don't need to be doing R&D on them particularly of significance, it's just developing the component base of the technology that we have. Other energy technologies, don't know what else to call it other than other. People have asked, you have asked for items such as ocean energy, lightning energy, electric power transmission distribution, smart grids, Keystone Pipeline, solar wind, electric energy storage, and solar wind backup power to be addressed. We don't have time to go into all of those. Essentially, most of these are not being deployed. Smart grid is an exception, and maybe Keystone Pipeline will be implemented, who knows. But let's start with the beginning here and look at ocean energy, wave, tidal, and currents. I've looked at that many times, and there's a lot of analysis that's out there and available in that. The bottom line is that it's a dispersed form of energy. You got to cover a large area if you're trying to capture wave energy. Tidal energy many times will get in the way of navigation, currents, and that's caused by tides flow, and with currents flowing in and out due to tides. There's navigation issues, but the bigger problem is infrastructure and the robust system that you have to put in place to survive the 30-foot or so ocean waves that develop just seasonally, not due to hurricanes or storms, but just seasonal storms and activities. It requires robust systems. And I was born and grew up down in the southeastern coast of Florida near West Palm Beach, and the Gulf Stream is the closest to the coastline down there than any other place along the Atlantic seaboard where the Gulf Stream flows. And for probably 50 years, people, including the Navy, have gone out there and tried to put turbines in the Gulf Stream to capture some of that energy and to generate electricity. None of it to any avail because they will always break loose. And you just have to have incredibly robust structure to make them stay fixed. And all this is economics, and that's one thing I probably haven't mentioned enough is economics. We need to be deploying the renewable energy technologies, for instance, and oil-saving technologies that will save the most oil and the most CO2 emissions with a minimum capital investment and minimum cost. And in a free marketplace, which is what we have, given the restrictions and the policies, you'll come up with the least cost way to accomplish that. People have mentioned lightning. Lightning is so sporadic, both in time and location. It's just not practical. Electric power distribution and transmission. The smart grid is already being implemented essentially. Remote meter reading is part of the smart grid, and when you got dispersed power generation with photovoltaic systems on roofs or large privately owned wind farms that are distributed around your grid, you got a lot more generation out there that's dispersed. And you got to have a smart grid to control it and know when it's coming up and down, and it's varying with the wind, it's varying with the sunlight, etc. So that's something that's happening, and it requires a lot of effort for deployment and demonstration, but that's the mode we're in with the transmission and distribution. DC and versus AC, we use a lot of DC transmission today at very high voltage over longer distance, and even for offshore wind farms, they many times will convert the AC generated by the generator in the turbine to DC and pipe it underwater with DC power, and then convert it back to AC when it goes into the grid. Wireless technology for transmission. We use wireless transmission for information, and there's very little power to it. That's just several orders of magnitude less power than what would make it practical. And they can be used in some isolated cases, like powering wireless phones or wireless televisions or things. But as far as transmitting bulk power to power a home, I don't think that's in the cards. Keystone Pipeline, even, that's obviously a policy issue there. And there's some good assessments done by quality people with all the assumptions in it and stated, and that have looked at the CO2 emissions from oil that is produced from the tar sands up in Canada. And the oil coming out of the tar sands up in Canada do produce more CO2 than the ones in which we just drill a hole in the ground and the oil that comes up. But it does produce more global warming. Whether we should have the Keystone Pipeline is a permitting policy issue that everybody can have their own opinion on that. Solar, wind, electric energy storage is something that we really need if we're going to have a dominant amount of our electricity coming from solar and wind. But the economics of that today are just really far off. And we need to keep working on that, but this is not in the near-term deployment phase at any economical competitive situation that we are getting to with wind and solar power generation. But in that same line, the backup, but without the energy storage, and for solar and wind, then we have to have backup power so that when a cloud comes across our PV system or the wind slackens off for our wind power, that we got conventional dispatchable, we call it, power plants that can be cranked up and turned on to meet the power demand that people want. So that's just a quick rundown of some of those other, I call them, energy technologies. And we're at the end of the road here regarding this course, Energy 101. Sorry we didn't have time to cover more topics. Your posts were great, and the discussion was great. The one that created the most controversy was electric cars and CO2 emissions. I did that in order to make a point, and I was reacting to the zero emissions emblem that's on the back of every leaf. That is true with the proper assumptions. In other words, if you look at the tailpipe only, there are zero emissions coming out of the tailpipe because it doesn't have one. But when you look back at where they get their electrical power, you have to make a lot of assumptions, and I made some in my assessment that I think are reasonable from a national perspective, and that has to do with energy policy and is applicable today. Now, in the future, you can always create a scenario in which things will be worse or better. And locally, you can always create a specific state, for instance, that they save significant fuel, significant CO2. Other states it doesn't. But I think always in doing assessments and comparing technologies, you always need to look at apples to apples. And comparing a Leaf CO2 emissions with an SUV is an unfair comparison, because that you got a lot of options to replace the SUV for less fuel consumption and CO2 emissions than going to a Leaf. So I think you need to look at that. That has to do with changing our mix of types of vehicles that we have. And we certainly need to do that. Europe is the best place, example for that we can see. I consistently, when I'm over there, get 40 to 45 miles per gallon in a 5-passenger mid-sized car. Technologies here is not a technology issue again, it's a policy issue. So thank you. We'll do a wrap-up and summary next. Thank you.